Hello, class. Well, we've come to the end of Chapter 2. We're on Lesson 6, Inverse Variation. And we start off with a little cartoon. We have here a police officer who's pulled over someone and looks like he's given him a speed ticket. And he says, "But I couldn't have been going 70 miles an hour. I only left home 20 minutes ago." Now, you might say, well, what does one have to do with the other? Well, one has a lot to do with the other, particularly depending upon another vital piece of information, and it definitely would be the distance. If we knew the distance, we could certainly calculate how fast he was going because we can see how far he's traveled in a period of time. Okay, that's where we get miles per hour. So let's read on. It says here, the time that it takes someone to drive a certain distance is a function of the speed at which he or she drives. The faster the speed, the shorter the time. Suppose, for example, that a young man in this cartoon wants to travel 120 miles. The times that the trip would take at several different speeds are shown in this table. So we have here the average speed in miles per hour, and we have the time that it takes in hours. Okay. Now, as one of the variables in this function increases, the other decreases. Now, this is different. Let's go ahead and write these down. We have the average speed. So I'm just going to put here speed. And we also have the time. Okay. So let's take a look. If the speed were 20 miles per hour, it would take 6 hours. So that the time is in hours. So the speed is in miles per hour. Okay, we can always note that. Maybe we could put a little comma here, say speed in miles per hour, and time is in hours. Okay, so we have 20 and 6, but then when we increase the speed to 30, notice that we're decreasing the time that it takes. And naturally, the faster you go, the quicker you get there. Let's go to 40. Now it only took 3 hours. And he goes up to 50. And now it only took we have a decimal 2.4. Then at 60 miles per hour, that's 2 hours. And now we have 70 miles per hour, and that's 1.7. And lastly, we have 80 miles per hour, and that's 1.5. Okay, now if you've dealt with speed, distance, rates, and times, you might be able to spot some information here immediately to understand the distance, because there's a distance hidden in here. But let's keep reading on. It says, as one of the variables in this function increases, the other decreases. More specifically, if the average speed is doubled, the time it takes is halved. In other words, it takes half as much time. So let's show the example of that. Well, when 20 is doubled to 40, the time it takes goes from 6 to 3. So we can see there's a doubling effect and there's a halving effect. In other words, it's cut in half. Another one here would be 30 over to 60. So we double the speed and we go from 4 hours to only 2 hours. So we can see that that is happening here. So let's just remove these and let's read on. Now let's see. For example, if the average speed changes from 30 to 60 miles per hour, which we showed, then the time it takes to the trip takes changes from 4 hours to 2 hours. If the speed were tripled, the time would be divided in 3. We could see that here as well with 20 and 60. Right? We triple the speed and now we have 6. Now it's only 2, so we can see the correlation between tripling the speed and then dividing it by 3. Okay, so we see the 3's there. We saw the doubling, the 2's, and dividing by 2. Okay, so let's see. Let's move on now. Two variables that change in this way are said to be, or said to vary inversely. Okay, here's a new term for us. And the function relating to them is called an inverse variation. The time of the trip in this driving speed function is found by dividing the distance, 120 miles, by the average speed. Okay? So if we let x represent the average speed and y represent the time, well, we can write y is equal to 120 divided by x. Now, how do we know that the driving speed or the distance was 120? Well, if we look at, for instance, I think the easiest one might be, well, we can take actually any of these, but the decimals are usually tougher. But if we were going 20 miles per hour for 6 hours, we would multiply 6 times 20. That would give us 120. Notice the same would happen here. 30 miles, I'm driving 30 miles per hour. So the first hour, I drive 30. The second hour, I drive 30. That'd be 60 hours. 60 miles. Then I drive another 30. That would be 3. So that would be 90. Now I add 30 more. That would be my 4 hours. So it's 30 plus 30 plus 30 plus 30. That would equal 120. Again, we could just multiply them and do the same. We have the same here as 40 times 3, 60 times 2. And if you took these decimals and did the same multiplication, you would still come out with 120 miles. So if we know the time that you're going to travel and the speed, we can certainly find the distance just by multiplying. Okay, and we're going to learn quite a bit about the relationship between speed and time and distance. We can, if we have two of those, we can always find the third. So we have now this formula, y is equal to 120 divided by x. Now, what would a graph of this function look like? Well, I'm sorry, let's just go back. We're letting x represent the average speed. So if we were to just take a quick look here and say the average speed, we're going to make that x over here, right? Because that's the average speed and we're letting x represent that. So I'm just going to slip in a little x over here and I'm going to put a little y here for time. Does that work? Well, let's go back and say, well, what is my average speed? My average speed was 20. When I divide 120 by 20, I will get 6. Okay, so we can see how this definitely works. And if you plug in any of these numbers, and you'll definitely yield the other value corresponding to it on our table. So let's go back. Now, what would a graph of this function look like? Now, that's what we're interested in because we're dealing with inverse variations. We've dealt with direct variations, right? Linear functions. We know that those are straight lines. A direct variation starts at the origin, that would be here, and pretty much just comes straight out the middle. Okay. Now, a direct variation, a linear function could start anywhere. Okay. And, depending upon what that b value was, would determine where we're going to start in the y-intercept. But again, it would be a straight line. Now we have a different set of numbers, and instead of the numbers increasing as, well, let's say as x increases, we're normally seeing y increase, which is what gives us that straight line. Or at least remember, because there's a linear um, there's a linear property to what we're doing, and we already discussed that in the lessons, how one thing is affecting the other. For instance, the a variable is simply multiplying the x variable, okay? And so we would simply take the b variable and place it on the y graph, and that we knew that that would be where we would start. But in this case, we're doing something different because as we increase, this number is decreasing. So this graph is going to behave much differently than the other graphs that we were using. So now if we look, it says here, the graph shown in figure 1 below, which we're going to draw over here, includes the 7 points represented on the table. So why don't we go ahead and plot our points? So we know that, for instance, um, using our x and y. Now I've already created the scale here, and as you can see, it's not proportional, simply again because we would not have enough room to put 100 points, let's say, 100 units. So we are going to go ahead with 1 unit on the y axis going up, but we're going to go by tens across, okay? And I would also just mention that when you create a scale like this, as long as the units, for instance, you go, if this is 10 here, then this ought to be 20, and this ought to be 30. You shouldn't say, well, this is 10, I'll make this 30, I'll make this 40. The distance between each of these should be the same in terms of value of unit. So I started at 0, I went to 10. Well, that means every one of these lines ought to go up by 10. Likewise, I started with 1, I went up to 2. If I went 1, 5, 6, 15, again, you're creating you're actually changing it completely, and there's really no scale at that point. Okay, so just another thing I needed to mention there, even when you are going with different units. So let's go ahead and plot our points. So the first one was 20 across. That's our x value. Let me go and get my black marker here. And oops, we're going to start off with our first point. If we can just get the black marker. Okay, so the first point was 20, and we're going to go up to 6. So here would be our first point. Now I know there's a little bit of a difference. They were skipping lines on their units. I don't have that luxury. I don't have the room. So we're just going to go a unit of 1 per line. So our graph may look a little bit different. It sort of pushes it all together, but you're still going to see the same effect. Now let's go over to 30, and that would be 4. Okay, now if we just paused here and we stopped, and we saw connecting these dots, we would have a straight line, okay? But we have to connect a series of dots. Let's see where the next one takes us. Well, we have 40, and now it's 3. Now there's a big difference here already, because from this point, we moved over 1, and we had to go down 2 points. But now, we moved over 1, and we only went down 1. So I'm not seeing a straight line. If I tried to make a straight line, it would actually come straight down to here. It would not connect here. So this already is showing me that this is not a straight line. In fact, remember, there are values in between all these. We've only taken these specific values. But if we were to take, for instance, 25, where would that place us? If we were to take 21, if we were to take 32. So if we were to plot all these points, we would notice that it never really forms a straight line. It starts creating what will be a curve. So let's move over to 50, and our value at 50 is 2.4. So we're at 50, and let's see, we're going to go up to 2, and 0.4 is probably going to be somewhere around here, just slightly below 1/2, or the half, 2.5. So now we also see that this is really shrinking. Before we came down, we went over 1 and we came down 1, but now we went over 1 and we only came down 0.6 really. So this is starting to really curve here. Now let's go over to 60 and we find that it's 2. Again, a major change. We went over 1, but now that was just really that 0.4. So the number keeps shrinking in terms of how far we're coming down for every 10 that we move across. Now we'll go to 70 and we see it's 1.7, which is over here. It's almost between 1.5 and 2. All right, so, and again, now that's only 3.3 that we're moving down. We're moving over 10 each time, but each time that we move over 10, we're moving down slightly less. And when we get over to 80, we're at 1.5, which is, again, on our graph, it's almost negligible. You really can't see it perfectly. But you could see that this is not a straight line. If I were to get my ruler and try to draw a line from this point to this point, I would not include all my other points. if I try to sort of draw lines, I'm never really going to be able to do this. So we're not going to try to do it because it's really not a line, and at no point is there a line. There's always, in this graph, there's a curve. There's always a slight curve. There's never a point where you can really put a straight line. The property just isn't there. But it does challenge us to draw a curve. And I think you already know how bad I am at that, especially with this pen tablet. I could probably do it a lot better on a piece of paper. But I'm going to go ahead and try to connect these dots. Okay? So if we just read here, it says, it is evident that they do not lie on a straight line. Back to the top of page 97. If we use the equation to figure out additional points, such as 25, remember I mentioned, which is 4.8, 35 is 3.4, 90 is 1.3, 100 is 1.2, and join them with the others to make a smooth curve, we get the graph that's shown in figure 2. So why don't we try to draw our smooth curve? Okay, so just bear with me. Okay, and again, I don't think, oh, I already started off wrong. This is a lot trickier than it looks. And so I'm hoping I can sort of get this. Oh, I've lost my, there it is. We're gonna start up here, and we're just gonna make a weak attempt at connecting these on like a curve. Part of the challenge with a pen tablet is that you're limited in space, so you do run out of room, even though there's plenty of room on the screen. So that's a fairly decent attempt. We almost missed a point there, but it's a curve. It's no longer a straight line. And when you draw your graphs, we don't want to see uh, a line go into each one and almost look like it's a straight line connecting dots. There ought to be just a slight curve. So if you want to turn your paper around and sort of try to get that natural curve, if there's a special angle, try to do that. Try to show the curve. Do not just connect dots. Okay, and what I mean by that is do not do this. Okay. So the wrong way to draw this graph would be to take a straight line and then take another straight line. And if I see those angles, like this angle, I'm seeing that you're really just kind of drawing straight lines, okay? Really make every attempt to draw that curve. You're probably never going to be as bad as me, okay? So let's go back and draw that line. How's that? Maybe I need some practice here. And let's see, get my pen. So we're going to try to make this curve again. And, you know, they say practice makes perfect. Well, actually, practice makes permanent. So if I'm doing it wrong each time, I'm not really practicing to be perfect. Well, that one was better, but I missed these a little bit. And again, it's very hard unless I really make a sudden move. So close enough. We have a nice little curve. Now let's read on. It says, as they do for the other functions that we have studied, the equation and curve give a much more complete picture than do the original table and 7 points. Okay, so it helps to see the equation, all right, and the curve. They kind of tell us something in the relationship of the numbers. And if we're just looking at the table, we're just seeing a bunch of numbers. Okay, and I promise you that we're going to slowly move away from tables, and we're going to depend much more on these equations, on formulas, and let's just say, you know, on the graph itself. So in general, here's a definition. In general, inverse variation is a function, and let me get my pen here. We're going to have to write this one down. It is a function that has an equation in the form of y is equal to a over x. Okay, so now we have y is equal to a over x. So this is our third form, in which a is a constant number other than 0. Okay? So let's just take a quick look at what other forms we had. Okay. Oh, before we do, we can see the number a is called the constant of variation. And the graph of the inverse variation is a curve, as we can see here at the bottom in this figure on the right on page 97. So let's go back and we learned our first one we had was, let's just say, y is equal to ax, and that was a direct variation. Okay, linear function we wrote as y is equal to ax plus b. All right, and we know that a and b are constants, and now we are learning the inverse variation. Okay, the inverse variation, and that is written in the form y is equal to a over x, or a divided by x. Okay, so we're going to need to remember these. It's going to be very important to recognize these, particularly for your tests, and just, moving forward, these terms are important to know. You will be challenged to know what these are as you are challenged through our tests coming forward. What exactly are these things? And even in your midterm, there may be some questions regarding the terminology. Okay, so just remember these, or at least learn them well and be very familiar with them.